Professor Claudio Zannoni from Bologna.
Yeah. Right, very good.
And well, time to get real then, with the stick prediction.
Right. Yes. But first of all, let me thank the organizers, Argir, Valeri, Miha, who's not actually here at this moment, all the organizers for this opportunity to be here and participate in this very, very nice workshop. So today I try to take the title of the workshop literally and say something about complex materials, particularly a family of complex material, not the metallic, not the alloys made by atoms that we heard some beautiful talk, this martensitic or colloidal, but organic functional material that would be involved, for example, in a lot of common applications from displays, but also in the field of organic electronics, where you try to replace silicon with organic material, and that involves organic field effect transistors, photovoltaic, light emitting diodes, or sensors. So what do they have in common? Well, let me take a simple example, and I hope you are not offended because it's too simple, but if we take a transistor, a thin film transistor, then basically it's working by having a field applied to this gate, and then this will attract, for example, electron or vacancies, holes, if you like, toward this insulator surface and create a conduction channel, which means that if you then apply a voltage between the source and the drain, you will have a flow. So it's like a tap in a way. And why do it with organic? The idea, of course, is to do it with the possibility of having a number of advantages, including the flexibility. Now, you probably have seen the last few days that the first displays for phone which are foldable are coming out, so you can have a small one and then you replace it and you have an A4 type display. But there are very many other like applications where you can have, for example, flexible bandages that can send signal of sensor type for medical purposes or whatever. But anyway, there is a problem because to have the thing working, you need a semiconductor, not really an insulator, but something that can have a mobility of charge which is sufficient. And silicon is very high, and that's why it's used after all, in this respect, of the order of a number of hundreds of the significant unit, which is centimeter square volt per second here. Of course, silicon crystal is better than polysilicon, but it's still very high. While most organic materials are insulators, which means, in practical terms, numbers on this unit of the order of 10 to the minus 5, 10 to the minus 6. To be a semiconductor, you have to choose a proper organic, which has a pi electron system, pi conjugated system, typically, like this pentacene or these polythiophenes or other molecules, and then you can go to something kind of little below 1 or order of 1. And the reason is, this is a kind of cartoon, of course, we'll try to improve on the cartoon, that in systems like this, if you organize the molecule property, you can have sufficient hopping from one to the other. It's not, you don't create a valence band really, but you have significant hopping to have mobility. So these conjugated systems are kind of, if not essential, probably the best has been found until now. And if you look at this molecule, there is a striking similarity with the structure of many liquid crystal molecules or many liquid crystal systems we heard about. And indeed, some of the material that give liquid crystal phases are also reasonable organic semiconductors. So I'll take just a few examples, this oligophenyl, sexithiophene, or these indinofluorines, or discotic material. There is a kind of Well, interesting similarity between a discotic and a molecular wire, because they do self-assemble spontaneously, as we know, and you want that, because if you have a nano device, you're not got to have someone soldering the two parts of your system. You want to put molecules and then change the temperature or something so that they pile up and, for example, connect your two parts of the circuit of the system. And if you look at this kind of typical molecule, you can think, even though it's not completely correct, this core full of electrons, right, that is piling up as the building of a semiconductor system, not really a conductor, but certainly then this chain will act as the insulator, the plastic that you have around your copper wire. And indeed, these distances are the order of 20, 40 angstroms, while the distance between the pi system is only 3.5, is the typical thickness of a pi electron system. So even though it's a semiconductor, it's not a real conductor, the mobility of the charge is a couple of orders of magnitude larger in this direction with respect to the transversal one. So they are, in this sense, molecular wire. And the liquid crystallinity, or more generally the molecular organization, is very important. Look at that. So if you take this classical example of this triphenylene molecule that I just showed, and you take them in the isotropic phase, this temperature, they are just normal insulators. They are, if you look at the mobility in the unit that I mentioned before, is of the order of 10 to the minus 5. But just cool the system down, so the chemistry is the same. You just bring into the this particular liquid crystal state, which is a columnar state. The molecules pile up and form column, and you see the mobility has gone up a couple of orders of magnitude. And then if you go below a certain temperature where a more ordered, in this particular case, helical columnar structure is built, then the mobility goes up again. And if you were to go to a perfect crystal, it would go up again. So why not use perfect crystals? The point is that nearly impossible to form perfect crystals. And if you have discontinuities, domains, not with exactly the same orientation, so-called grain boundary condition, then your charge mobility is lost at that point and the material degrades completely. So you start to see that it would be nice to have design principle or techniques to try to optimize or anyway to predict this type of behavior and perhaps improve it. So these were discotic, but also the more classical rod-like liquid crystal, smectic, could be used. They do not have normally a very high mobility, actually it's rather poor, you see. But recently meaning less than 5 years ago, some interesting families have been discovered, particularly these are called BT-BT. That's the nomenclature is not my strength for sure, but I don't think it's interesting anyway. But if you look, this system have a behavior that goes through from a liquid to a smectic layer structure to a more ordered smectic or smectic E, and eventually crystal. So the mobility in these phases, found particularly by the group of Professor Hanna, but also in Europe by Yves Geertz, for example, and surely there will be other groups around. These are very fashionable material. Now, you see the mobility is claimed to be of the order of nearly silicon, I mean 10, 100, huge. And we still do not understand exactly why. Even though one of the possibilities seems that going through the liquid crystal phases, you can prepare the system, teach the system to become a crystal, as it were, eliminating away the grain boundary before you form the crystal. So if we want to model and try to understand something of this system, we do have various problems. One is to try and predict the molecular organization in those particular conditions. The other is to calculate the charge mobility. And the most typical calculation of the charge mobility, without going into many detail, requires actually atomistic level detail of the organization, not just the fact that the molecule are liquid crystals or whatever. Because in the more common model, which is based on Marcus' theory from Nobel Prize Marcus, is a hopping mechanism where the probability, if you like, the kinetic of going from molecule or site I to site J is given by a bunch of parameters, but basically, apart from temperature, by this transfer integral that tells you how well the wave function of one molecule that in that particular moment acts as a donor is overlapping and talking to the wave function of another one. So that particular thing, this Vij here, that appears square here, will depend, for example, if you have two molecules, one on top of each other, on just on the rotation of either one molecule with respect to the other, or of course on the position of one molecule with respect to the other. So you really have to go for this particular type of calculation into really fine details on the structure. Now you could say, okay, if I've got the mobility, the hopping rate between two molecules, how do I calculate the probability that the charge that starts at this side will reach the electrode at the other side? Well, the way it is simulated is relatively simple. It is normally called, what is normally used, a method which is a kinetic Monte Carlo, whereby you extract, now you know the K, A, J, because you've calculated them from quantum mechanics and molecular organization. Now you just calculate the probability that the charge sitting here hops into another one, hops into another one, hops into another one, with a Monte Carlo procedure going with random number, and you make a very large number of hoppings until your charge either dies because it's taken by a trap or goes the other way around, but with the help of a field applied, it may reach the other side at a distance dn, and then you just calculate the time it has taken. So to calculate this mobility, you need detailed molecular organization, you need atomic stick position, and that is a problem. We cannot do generic simulation with, balls or spherocylinders or whatever. And the surface is very important, because if we want to have a device, for example, in this textbook picture, say a type of transistor like the one I mentioned before, and we want to make it with this-like molecule, if this is the source where the electrons come in, and this is the drain where they come out, well, we would like the pi system to be organized in this direction, right? So we want the molecule to be perpendicular, right, to be side with respect to the surface. But if we are trying to devise, sorry the pun, to make a device, not devise a device, that, for example, should collect photons for a prototype solar cell where you have donors and acceptors molecule here in these columns, or vice versa, if we have to put photon emitters and we have to have an OLED light-emitting diode, like you have in many practical devices now, we want the molecule to be the other way around with respect to the surface. So rather than being edge on, we want them flat on. So it is important to know the molecular organization, for example, between the molecules that act in an organic solar cell, either donor or receptors. And without going into the details, I would like to stress that it is important then to try to understand what happens at the molecules near a surface of some kind, because the type of orientation of the molecule we would like to predict. So anchoring, say, we would like also to know if the order of the molecule, which is so typical of a liquid crystal, the tendency to be parallel to each other, is reinforced or weakened at the surface. Are the molecules more ordered or less ordered close to a surface? And once again, I do stress that this is important, because these devices that I mentioned, I mean, the thickest one are the displays that we heard of a few microns, but if you have organic electronic application in mind, typically you have films of the order of tens or hundreds of nanometers. So they are thin, and if they are thin, the surfaces and their effects are more important. So then also transport properties and dynamic may change for the surface. Well, so again, how important is the chemical nature of the surface? How important is the morphology? So if, for example, we have liquid crystal or functional material close to silica, now silica could be quartz or it could be glass. Is that important? Is it just the chemistry, or is it the morphology as well? And what about the roughness? And more or less, in all these cases, can we make prediction? So if we were to do a real experiment, what could we imagine as a roadmap? Well, we would need a material, a liquid crystal or another functional material. That's one. So we would have to synthesize it, or maybe buy it if it is available and we are lucky. And then we would need a surface, right? And again, we would need to prepare that, either theoretically, computationally, or synthetically, and we would need to deposit the material on the surface and then characterize it. And we're going to do the same. Actually, that's what we've done. So rather than buying the materials or synthesizing them in the lab, we can, and I will explain what I mean, synthesize them in silico, if you like, with the computer. What does it mean? That you start from a well-defined chemical formula and you try to predict the properties. Predict the properties means predicting, for example, if it will be enigmatic at room temperature, a liquid crystal or not, or predict, the order parameter, the diffusion, the whatever. And of course, you have so many. This is a little library that we have studied, and for each one of these, we have reprints in case you are interested. And if you are too shy to ask, you just go to my website, which is easy to find, and you can either download the reprint or find the DOE to download it. So, for example, the quinquephenyl that I mentioned before, and I'll say something more about that, cyanobiphenyls, which are the kind of fruit fly of liquid crystal. There are thousands, literally thousands of papers on cyanobiphenyls, and you can find them in your displays, and this discotic molecule that I mentioned before. So this we have done. And what is the synthesis? The synthesis means start from this chemical formula, do some quantum mechanics, quantum chemistry, which is now reasonably standard, using some DFT method or better, and then you get the geometry. This color here represents the partial charge on every atom, because even though the molecule is neutral, every atom has a different pulling strength with respect to the electron, a different electronegativity. So there is a different partial charge, and that is very important. Then the molecule can be thought of having different fragments that can rotate or anyway be flexible, and then this will involve some torsional potential that can be determined again. And then you want to determine the interaction of one fragment of a molecule with one other fragment of another molecule, and you have to build this set of interaction, which is called the force field. At this point, you can have all the information necessary to solve Newton's equation of motion for every atom in the system. And these atoms could be of the order of kind of 100,000 atoms, 100,000 little spheres that have to be evolved in time. So this is simple in principle, but it can easily take, for the molecules of this complexity, for a set of temperature necessary to locate the phase transition, can take sort of order of magnitude of 100 years of one processor. But of course now you use parallel computing with maybe hundreds of processors or thousands of processors, and if you manage to distribute the work in this parallel computing sense, then it will take a more manageable time, but still many weeks or months. Okay, you could say, so what? It's so complicated. But remember that if we were to look at the charge of increase of performance in computer of the last 20 years, the computing power has increased of a factor of 10 to the fourth, 10,000. My smartphone or your smartphone is more powerful in terms of megaflops of number of operations per second than a supercomputer of 30 years ago was. So if the trend increases, then what our task is to prove that it's doable, not that it's doable fast now, is to show that it can be done. And then if people that build computer or anyway are maintaining the trend, maybe you young people will be able to use that in the lab. Like now, every chemist has a PC, a portable computer, and can do quantum chemical calculation on a single molecule. So the way you do it is really rather simple. You identify all the different type of interaction. For example, these are bonds, so they will stretch or bend, dihedral. Everyone has an energy tag attached. and then you have this intramolecular part, and then you have non-bonded. So one atom of one molecule will talk to the other molecule atoms by these attractive dispersion forces, van der Waal, induced dipole. It will not want to overlap with the other, so they will repel each other with this term. This is Lennard-Jones for, familiar. And then you'll have the electrostatic interaction, which have this Coulomb form. You need some trick to calculate this sum because it's not convergent, but there are tricks called Ewald summation, which are totally standard. So now often, when you have liquid crystal, there is a temptation to consider them as very simple objects, like rods, etc. And for example, Ed Samulski, who is a very well-known liquid crystal scientist, suggested that this quinquephenyl, apart from being interested for organic electronic applications that we were, is also kind of the true best approximation to a really rod-like molecule. So we couldn't resist the challenge, and then we did atomistic on this. So we worked out, the details are useless because you can find them in the paper, but just to give you an idea of the steps, we worked out the torsional potential, how easy one of the phenyl can rotate with respect to the other, and you can do that different level of theory, but the basic structure you see is similar. So the phenyl are twisted of around 40 degrees, at least in the gas phase. They will squeeze a little bit in the liquid. But you have to tune the potential because, the interaction between two molecules are also affected by all the other molecules that you do not consider. And that goes, for example, in having an effective well depth for example, the carbon-carbon interaction that I showed you before. I'm just showing this because the temptation could be of using or pushing a button. You can easily download force field or even programs from the net or buy them. And some of the most famous ones are these Amber or Charm. And if you use that program without tuning, with their parameters, you don't even get the density of the system right, let alone all the other properties. So 0.06 is here, the experimental density is here. If you use the best quantum chemical calculation for two molecules in the gas phase at 0 degree K, they are even outside this band. So you have to tune one parameter in this case and get all the properties. But this is, so the message is, do not just download something and use it. The transition temperature, which are your first observable, because you want to know when the material will melt, etc., may well typically be wrong of something like 100 degrees or more, which is not ideal. And then, of course, you can calculate ordering matrix, you can calculate this Q tensor that we heard quite a lot about, you can diagonalize it and get order parameter and directors. Okay, this is not the time. So if we do it for quinquephenyl, we predict, or anyway find that there should be a transition here somewhere at this very high temperature, because it's a very stable system to disorder, and then a nematic, and then smectic A, molecule perpendicular to the layer. So that's the first level. What does experiment says? That is, again, I'm saying this just because it's amazing, isn't it? When you say compare with experiment, you assume that you go to an experimental paper, read off a number, and you take that for being correct, right? But now if we look at 1, 2, 3, 4, 5, some from Nobel Prize fame even, experimental papers, we see that the transition changes from, well, what, 5, 6 degrees or more, 98 to 70, etc., which you say, well, it's not very much. We are worse, we are off by 10 degrees at least, but it's not satisfactory. If you measure your body temperature, you want at least a 0.1 degree before you call the doctor, because if you call the doctor, you say my body temperature is 37 degrees C, but it could be 42, then he probably won't be happy with you. And this is very disappointing and showing that really, even for very well-defined system, nobody in the world at the moment can calculate things like transition temperature, which are apparently simple, but for the theoretician they are not, because they are derivative of a two-particle correlation function, which involve four-particle correlation, which are tricky. But anyway, you can get, we can get it into a few degrees, and we compare favorably with a variety of experiments, magnetic resonance, wide-angle scattering, birefringence, diamagnetic. This is not the place to give an idea. I just want to attract your attention to the fact that these red curves, which are the common Mayer-Sauper field theory, do not work particularly well. And what about assuming it's a rod-like? I mean, the reference calculations were done by Dan, which I don't think is in the audience, but anyway, here in Cambridge. No, actually in Amsterdam he was at the time, long time ago. And there's no reason why this should be exactly a spherocylinder, but you would, according to Samoursky, or anyway to the idea. They predicted in those days that for an aspect ratio, length to breadth ratio, like the one we have here, you should not have, not only with on-Sager mean field, but also with the best simulations, you should not have enematic or asmactic, but should go from crystal to isotropic and have a coexistence. But the molecules don't know, and actually they have asmactic and they have enematic, which is fair. Why? Because it's not really so rigid as spherocylinder. So if we plot, for example, the bending angle of this quinquephenyl, surprisingly, it's not a delta function. It's not just a zero angle, but you have a distribution which is non-negligible, and that changes the aspect ratio. So maybe there is no really rigid rod molecule. I just, for the liquid crystal practitioner, I'm just adding that what we find are two symmetric A. Why should there be two symmetric A? What's the meaning anyway? Well, what we mean is that for a certain range of temperature, this is a symmetric A, structure-wise, the diffusion tensor is, let me say, so if we have a symmetric, at least according to the textbook picture, you would imagine that movement in the layer is what, faster or slower than the moving across the layer? Faster. If you have layer, it should be easier to move in the layer plane rather than across. This is not so for a number of liquid crystal, but also is not in this particular case. It seems, according to our calculation anyway, it's not been found, it's not been studied experimentally, that in this case, close to a crystal, in the low temperature one, diffusion is actually faster in the plane, according to the classic textbook picture. But in this other range, while the structure remains the same, it's actually easier to jump from one layer to the other than in the layer. So this textbook picture maybe should at some stage be improved. And then you go nematic, where clearly the diffusion is easier along the axis. Now, we've done this for cyanobiphenyl because we wanted really to have a comparison with simulation. And cyanobiphenyl, this family, if you have a chain which is 1, 2, 3, 4 CH2, you have no liquid crystal. When you get up to 5, you have a liquid crystal, and then 6, 7, 8 gives the first symmetric. And our simulation in this case are within 3 degrees from experiment. So that's okay. We can say that we have synthesized, computer synthesized cyanobiphenyl. The properties will spare you the bothering of looking through comparison with experiments, because again this is published, but it is satisfactory even for detailed atomistic results like NMR, like the order of this bond or that bond, we can predict without any further fitting. So now we can think that we have synthesized, computer synthesized a liquid crystal. Now we need a surface. What surface? Well, when we think of surface, we think of something which is really flat, like this one, isn't it? Something like the thing described in this delightful little book of Abbott, where imagine people living in flat land, two-dimensional people living in two-dimensional world, which is still worth reading. And this was the view even of extremely famous scientists like Langmuir, because of course it is true that if you look at the surface of glass, it looks flat, two-dimensionally flat. But if you look at atomistic level, this is actually silica at atomistic level. So there is a roughness in the sense of a mean square elevation which is non-zero. And you call a surface atomistically flat if this roughness is of the order of the diameter of the atoms. But experimentally, it could well be more. So we studied a few surfaces: silicon terminated with hydrogen, silica quartz, silica glass, fullerene. This you can call hard surfaces. And we've also simulated in detail some self-assembled monolayers made by long chain molecules that are attached covalently, typically, to the surface here. So alkysilane or fluoroalkylsilane, or some polymers. And you know that in polymers, the idea is that if you rub a polymer, then the liquid crystal molecule on top will align according to the rubbing direction or lapping direction if you are softer. We want to I just quickly show you some results. So this is atomistic 5Cb on silicon crystal, and this was done for two thickness, 10 nanometer or 20 nanometer thick film. This is a 6 by 6 nanometer slab with a certain depth, of course. And now the two temperatures for the thicker film that ends up here. This is the thickness here, and this is the order parameter. And this is, of course, the thinner film. Two temperatures, isotropic and nematic. And what you notice is, first result, that all four curves are essentially the same at the surface, which indicates that the order at the surface is not determined so much by the temperature, etc. The thickness of the film is really determined by the surface interaction. And moreover, it is, in this case, for a crystalline substrate higher at the surface than, I don't dare to call it in the bulk, but in the middle of the film. So, then if we take silica, and we can have it in the crystal form, we took cristobalite, which is one of the many, or glass. This glass has a root mean square elevation. The bumps in the surface are of the order 1.5 angstrom, and this 3 angstrom. You could say this is a theoretician roughness. This is too small for reality, but not true. You can buy glass, the one that is used to support magnetic particle in hard disk, for example, which is actually with this root mean square roughness. So this is a picture. This is topographic map, and this is an electrostatic map of the field close to the surface. And now again, two thicknesses, two temperature, only one thickness, 20 nanometer, and this is for the crystalline, and this is for the rough glass. What do you notice? Well, you notice that again for the crystalline, actually in all cases, the order at the surface is essentially the same, so it's surface dominated. But if the surface is crystalline like before, the order is higher. If the surface instead is glassy, disordered, degenerate in two dimensions, the order is lower. So if you have to plan a material for a design, and the quality of your device depends on, for example, the contrast depends on the order at the surface, then the recommendation would be to have some sort of treatment of your surface, for example, thermal treatment that would enhance crystallinity of the surface, and or vice versa. And then with soft, we've studied this in collaboration with people doing real organic, people at IMEC in Belgium, which they actually make real things. And it's very difficult to tune the surface of insulator or electrode for that matter, but in this case insulator. And one of the ways they use it is to cover the surface with this long chain. So we did study silica, which is the insulator, with added this self-assembled monolayer, either alkylated or fluorinated. Notice that the alkylated one are tilted with respect to the surface, and this is true in reality. The fluorinated instead stand out. And on top, pentacene, which is a classical semiconductor. And of course, well, not of course, but we see that if we have the fluorinated anthracene, which is an electron attractor, you modify the attractivity of the surface for the holes. Pentacene is a hole conductor, and then you change the work function of the surface. And again, not to go into detail, but to say that you have the information to predict the changes. We try to look also at a condition for inducing, rather than planar alignment of a liquid crystal or a functional material at the surface like we had before, alignment perpendicular to the surface, which is called hometropic. And in practice, people have used molecules similar to this, lecithines, which have two chains rather than one, but similar to this, or even this is self-assembled monolayer to induce perpendicular order. But this is strange, isn't it? If you use this and it is tilted, why should you get 90 degree if you start with a surface which is combed in this direction, which is pre-tilt? Well, you can study this again with atomistic simulation, and we looked at different self-assembled monolayer, and the message here is, if you take the self-assembled monolayer at full coverage, that is, you have molecules in contact with each other, you know, it's like trying to align. Just let me make an example for the students anyway. Suppose you want to align a pencil planar with respect to the surface. That's not difficult, isn't it? You just leave it on the surface. But if you want to align it perpendicular, how could you do it? Well, one way, you go to your bathroom, you find a brush, right? And then you put the pencil on the brush. And and the pencil will be aligned by the brush, and it will be perpendicular to the surface on which the brush is attached. So you could say, well, that's easy. This is the brush, and the molecule should align perpendicularly, but they don't really necessarily do so. If the brush is too dense, you can imagine that the pencil doesn't go in between the brushes, as it were, but just sits flat, which is exactly what happens here. So you could reduce the density of the brush, but that's not so easy to do experimentally. The other trick that we thought, and is actually used by experimentalists, is to have a mixture of long and short brushes, and you put them at full coverage. But since you have these short brushes, they will create kind of holes that will align the pencil, the molecules. And if the molecules do penetrate, actually they straighten the angle. So the molecules that at full coverage were still tilted, now, and you see this is full coverage, the molecule of 5Cb, which are the one on top with the nitrogen, the blue spot there, aligns flat. In this condition with long and short, some of them do penetrate, you see, they go and try to touch the silica, and then they actually straighten the comb, as it were, or the brush. So the self-assembled monolayer, which was tilted without the 5Cb, is now becoming at 90 degrees. So you also kind of understand how this happens. And now I have two more examples if I still have 5 minutes, isn't it? Yes. 7 minutes, ample. Oh, sort of. So now I mentioned before that the kind of common technique that is used to align a reasonably thin layer, a few micron layer of liquid crystal, is just to maybe cover the surface with a polymer and just rub the polymer or lap the polymer. The idea is that, well, nobody knows. If you look at the old book, it shows ditches and the molecule going into the ditches and being aligned. But the molecules are only a few, say 1 nanometer thick. They're long, but you know, so how can you, just by rubbing with a cloth, like it's used, make ditches which have that nanometer? You probably make micron-sized grooves. But anyway, the idea is that you align, like that's the cartoon I was mentioning. It's nice, but it would work with logs, but with molecules, it's not obvious. The other idea is that the chains are aligned, and then by some sort of attraction, you get also the liquid crystal molecule to follow the alignment of the chains, which could be. But then they should all behave in the same way. But if you take two common polymers, polystyrene, which is this one, obviously replicated, or PMMA. PMMA is the kind of transparent, glassy-looking plastic that you cover your CD, if you still have CDs around. Then the behavior is different. Experimentally, it has been found that rubbing in this direction will give an alignment of the liquid crystal along the rubbing for PMMA, but for polystyrene, in a number of cases, the alignment is perpendicular, which is strange, isn't it? You rub in this direction and the molecule align in the other. So why is it? So we did a simulation, or more than one, by combing the chains of the polymer, which are of this sandwich here, right here and here, of polystyrene or of PMMA, and we took a disordered surface of polystyrene and PMMA and the combed one. And now if we look at the order of the liquid crystal trapped in between, which is the usual cyanobiphenyl, you would expect that, well, I think, let's see. If we have the disordered glassy surfaces, the order is of the bottom and top surfaces kind of unrelated. Why should they be? They're just random. And but if you take the ordered one, right? If you take the ordered one, the rubbing is in this direction. You would expect the ordering to follow the rubbing, and this is happening. This is the bottom, and this is the surf direction of ordering. This is happening for PMMA, but for polystyrene, like found experimentally, it is perpendicular. And why is it? It is clear, looking at the atomistic simulation, because of the structure of this phenyl ring coming out. When you pull the chains, or order the chain some way, you form kind of molecular corridor which can host the liquid crystal. And you see the phenyl is perpendicular to the backbone, so if you align in this direction, it's actually quite reasonable that you get the alignment in the perpendicular. So you see, you can explain an experimental non-obvious fact by looking at the detail of the structure. So align in this way, PMMA follows, so 5CB on PMMA follows, 5CB on polystyrene goes perpendicular. And now in the last 3 minutes, I want to go back to organic electronic application, because I've left them aside a little bit. Now I think, I hope, we have to have, if not convinced you, at least suggested to you that if we do detailed atomistic simulation, we can go and predict properties in detail, transition properties, and well, also order, well, I didn't, mobility, dielectric constant, but the problem is that if we go to our organic electronic application, this is, for example, an OLED stack, we have a stack of films which are 50 nanometer, 10, 20, 30. In other words, we have to have many more molecules that we can possibly afford at this moment in time for a full atomistic simulation. But then, as I said at the beginning, if we want to calculate charge mobility, we need detailed, atomistic detail. So how do we do that? Well, the idea is that maybe to predict the molecular organization, we can coarse grain, we can give up some of the detail, right? And this is something that is done often in biophysics, for example. There are this coarse graining, one of the most famous one is Martini, but there are a number, where a bunch of atoms is mapped into a sphere, or many spheres, which is fine, except we don't particularly like it for our application, because if I look at many common molecules, not all of them will be liquid crystal, many will not be liquid crystal, but they have a feature in common, which is one I alluded to at the beginning, which is they have conjugated pi system, electronic system. So they are made by fragments that are individually flat, and then maybe they are rotated one with respect to each other. So we have, this is just data I'm sharing, very recent one, is we are proposing a modeling in terms not of spheres, but in terms of ellipsoids, which are individually mimicking the parts, the fragment of the molecules that are conjugated. And we want this modeling to be reversible, because we want to predict the molecular organization, and we want to reverse back to the atoms, and then do the calculation of the charge mobility. So let me give you some more details. So we have the all-atom representation, like in the simulation I showed you before, and we can do a simulation of, say, 1,000 molecules, sort of. Every molecule will contain order of magnitude of 100 to a couple of hundred, few hundred atoms. So this is already a substantial simulation, but doable. And then we coarse grain in a parallel way by taking, I'll show you some specific example, by dividing this molecule. There's more than one way of doing it, but dividing it with some common chemical sense, dividing it into bits, and these bits will be free to rotate according to a certain potential that we have to define. And we make again a simulation of the order, or same order. We can use this now to check that the parameters that we have used here are okay. When we are satisfied that this is okay, we can upscale this and simulate big samples of the order of 1 million molecules that you could not do by atomistic. And once we've done that, we can, when we have done the coarse graining, we have not lost the atoms. The atoms have been left, sorry, I wanted to show you, yeah. The atoms are still there at well-defined position inside this ellipsoid. We can come back, revert to the atomistic, and do the calculation of charges. So the coarse grain is done in terms of ellipsoid that are attractive and repulsive, so Gay-Berne, very common in liquid crystal. Then we have Coulombic between charges that will be placed inside this ellipsoid so as to reproduce the electrostatic field. And then we have torsional potential for the inside. So this is an isotropic bead, will be a biaxial ellipsoid, because every bead is not a sphere. And I quickly go to the charges. We have developed already a genetic algorithm to reproduce the electrostatic field around the molecule with a minimal set of charges that give the same electrostatic potential to within a threshold. And this is an example, for example, for these few molecules here. The model is fully anisotropic, and this is some results. So this is one of these molecules. This is its representation. It's already complex, and there is some maths to do. All the orientation is in terms of quaternions, and this quaternion potential have to be developed, but we've done it. So the molecule can fully move and rotate, and we can do, this is one of the most important one, alpha and PD. We see that the density from the coarse grain and the atomistic comes very close to a 10% or less. The G of R that were discussed in some previous talk are reasonably well reproduced between the atomistic and the back mapped coarse grain. And this is actually the 1 million samples. The color here represents the orientation of the beads with respect to this 3D palette. And we've done it also with molecules that are, pretty complicated, I would say, by any guess, like this. And actually we're building a little library of molecules that are good organic semiconductors. So this brings me to the conclusion. I hope I showed you first that the atomistic simulation with some suitably optimized force field can predict reasonable values for morphologies, for properties, or the parameters, whatever. That surface anchoring can start to be predicted. And then we can, by this reversible coarse grain simulation, produce organization that are similar to the one produced by full atomistic detail. And maybe going back to the title of the workshop, optimal design, we are not yet, I don't think, in a position of really predicting what is the best material setter. But we are in a position to start to answer a question that, for example, in European project is posed to us by industry. It is, okay, we understand that you cannot tell us what is the best material, but if we give you 10, 20, 50 molecular structure, can you tell us which is the best between this? In other words, which is the best candidate between? And I think we have made progress in this direction toward the vision that is of actually simulating from the molecular details of the production process, the device, and the property of the full thing. Let me just thank the people that have been involved most in the work, Otello Roscioni, Matteo Ricci and Lara Quercegrosse for this reversible coarse grain, Roberto for this Gay-Berne, Luca for the atomistics in general, and Silvia for again Gay-Berne, Mattia for surfaces, and Antonio also for the atomistic, and last but not least the agencies, and very last and not very least at all, you for your kind attention. Thank you.
Yeah, I was just wondering, with your homeotropic alignment, when you've got your close packed and your less close packed, going from planar to homeotropic, using the smaller chains, can you start to think about tuning the anchoring strength, things like this? Or do you measure that?
We have measured the anchoring potential, well, it's a bit too noisy for that, but we've measured it. The way we measure it is we calculate the probability of finding a molecule at a certain orientation from histograms of the experimental simulated data. We do inverse Boltzmann for that, and we get an effective potential acting on the molecule, alla Rapini popular. What we find normally is that the anchoring strength is much higher than what was measured some time ago, and actually close to what has been measured recently with atomistic. As we think that the reason is that the anchoring strength decreases very quickly moving away from the surface. So in many of the old measurements, the measurements were actually on a scale that was, was actually making the surface a coated surface, if you like. So a renormalized surface by the first few layers of the liquid crystal. But the answer is yes. I think the value that we find are really close to a surface, and the anchoring changes dramatically, more kind of 2 orders of magnitude in 50 nanometers. So, yeah. So when
it didn't seem to me that your estimate for the transition temperature of quinquephenol was that bad. I mean, you were complaining about a 10-degree difference. Do you not suspect that some of the experiments at those temperatures are perhaps a bit unreliable as well? I mean,
yeah,
you get decomposition and...
Yeah, absolutely. Indeed, the fact that the different experiments were already different one from the other of the order of 7-8 degrees is an indication of that.
Yeah.
Because people that do phase transition critical exponent of very simple material go up to 10 to the minus 3, 10 to the minus 4 degree.
Well, yes, but not
so,
at the point where the material is decomposing.
No. Sure, absolutely. But if I have to speak against myself, I would say that since there are these experimental difficulties and our molecules do not decompose,
yeah,
then if we had 10 times more computer power, we could, by exactly the same mean, get a bound on the transition, maybe, I'm sure, of a couple of degrees. And that would be probably better than experiment. So there are situations where, having tuned everything else, you can actually beat experiment, for sure. I can show you example where our prediction for order parameter was a bit for P4 was a bit different from experiment, and then people, group of Gisselman, Misha, you were part of that paper, redid the measurement by depolarized Raman scattering of a better quality, more modern, and the new values, experimental value, actually come close to simulation values. So yeah, I think it's getting to the point where it is robust enough and to be reliable.
Okay, so let's thank our speaker again.